So, uh, let me just introduce myself at the beginning. My name is Nasser Hasan. I'm a doctoral student at the Research, Measurement, and Evaluation in Education program at the School of Education at UM. So today I'm going to present this webinar about performing multiple regression through SPSS for your data set and research as well. So just kind of a general overview. In this webinar, I'm actually going to cover, give you actually a kind of brief introduction to multiple linear regression concept, and in which we will talk about how we will do a model specification. And we will also talk about some of the assumptions and how to assess them through SPSS as well. And the second part of this webinar is going to be about running the real analysis through SPSS. I'm going to do one example, and I will leave an exercise for you guys to play with it at the very end of the webinar. And I'm going to introduce the idea of selecting predictors or variables for your model. And remember that you are always welcome to ask any question when it's time to question. I will do my best to be a very slow and to express everything in a very well details. So just feel free to ask any question if you have during my presentation. So let's get started. Of course, if we want to talk about multiple linear regression, we should introduce the simple linear regression idea at the beginning. So the simple linear regression is carried out to estimate the relationship between a dependent variable, in this case it's y, and a single predictor variable, which is x. In every regression model, the predictor cannot explain the whole relationship or the variance in the dependent variable. So there is always a measurement error or residuals. So you will see that in every model, we should have some sort of error, even though we pick the best predictors in our model. So multiple linear regression it's just like a general idea about the linear regression or general formula of linear regression. So a multiple linear regression is carried out for two purposes. First, to predict the values of a dependent variables, giving a set of predictor variables. In the simple linear regression, we have only a single predictor, where in the multiple linear regression, we have more than one predictor. And remember, always there is an error. And the second purpose of using multiple linear regression technique in your analysis is to determine which variables are the best predictors for your model. And I'm going to talk about this just at the end. So let's move to the assumptions that you should assess when you want to run any multiple linear regression analyses. We have kind of 6 assumptions that we should check before moving to do any analysis. But SPSS is actually doing this with the analysis. So don't bother yourself thinking about how to perform these assumptions or how to assess them. We are going to cover all of them when we do the analysis, and you will see the outputs from SPSS. So the first assumption is the normality assumption. And by saying normality, we mean that the residuals or error terms should be normally distributed with a mean of 0 and a constant standard deviation or variance. The second assumption will be the homoscedasticity assumption. And we mean that the variance of the residual or error terms should be the same at each level of predictor variables. The third assumption is the independence. So all of the observations are independent. So this should be met when you collect the data set, or you are in the collecting data set stage. The fourth assumption is the independent errors, and that is for any two observations, the error terms should not be related. So the coefficient, the correlation coefficient between the error terms for these two observations should be approximately equal to 0. Any violation of this assumption will cause a term, we call it an autocorrelation problem, and we will talk about it when the time comes for this, especially when we talk about the SPSS outputs. The fifth assumption is the linearity assumption, and that is the relationship between the dependent variable and each independent variable should be linear relationship. So you can assess this through scatter plots in SPSS. And the sixth assumption is that there should not be any perfect collinearity. And we will also talk about the concept of collinearity when it comes in the SPSS output. But just briefly just generally speaking, collinearity means that the predictors themselves are correlated with each other. So let's assume we have two predictors, X and Z. If they are perfectly correlated with each other, so in what sense we should add both of them in our model? They are kind of the same, since that they are perfectly correlated with each other. So adding both of them will not do anything for our model. So this is why we care about the collinearity when we want to do the analysis in SPSS. So this is generally speaking about the idea, the concept of multiple regression. I know it was super fast because I want to spend more time doing the analysis than just introducing the concepts for you guys. I'm assuming that everyone at least should be familiar with what I've said already. So just ask me a question if you have any. Otherwise, we will move to the real goal of this webinar. You can either ask a question in the Q&A button or the chat as well. I'll be looking at both. I assume that there is no questions, so let's move. Before doing any analysis, I will ask you please to download this data set from this link. I will give you about 5 minutes to do that, please. And then we will start from there. Can I copy the link here? Sure, let me see if there is any way to do that. Okay, hello. And here is the link. Is everyone able to see the link in the chat? Oh, I'm sorry. I should post it for attendees. So I think you should be able to see the link now. Mm-hmm. Just another couple of minutes to download the dataset. I got a question about the previous two meetings or webinars. I don't think they were recorded. However, you can access the material through our website, the Statistical Supporting Unit at the University of Miami website. You will be able to download the PDFs or any related material. However, for this webinar, it will be recorded and then uploaded somewhere. Okay, just one more minute, and excuse me for that. I hope everyone is ready to do some fun through SPSS. Okay, so let's get started. If you download the data set, you should be able to open it in SPSS. And you can see that there are 4 variables from 20 students that are related to their performance on exam. So the 4 variables are the score, which is the exam score. If you can see the labels here. And it's a scale measure, which is ratio. I mean, SPSS is not defining ratio, is not differentiating between ratio and interval scale. So they are both scale in SPSS an SPSS point of view. So, oh, you don't see my SPSS screen. Does anyone have any access to my, or can see my SPSS screen? Or it's not showing? Oh, okay. Let me, I see. Makes sense. So let's do this. A new share and then SPSS statistics. So what about now? Can you see both of them? Okay, great. Good. So yeah, by looking at the SPSS window, you can see that we have 4 variables. The first one is the score, which is the exam score. The second one is hours, which is the hours spent revising. and the third one is the anxiety scores, and the fourth one is the A points. A points is kind of something in the United Kingdom's educational system. It's just like a certificate that the student gets when he want to apply. I'm not sure, but I'm assuming that this is just kind of a certificate that they give to the students if they want to apply for any college or school. All of them are on the scale measure. So I think this is all we want to say about the, I think this is all what I want to say about the data set. So in this example, we want to determine whether our spent revising and anxiety scores and A-level points, entry points, have any effect on exam scores. So our dependent variable here will be the exam scores, and all others will be predictors or independent variables. So if you can, if we want to draw this as a regression model, you can see that our dependent variable, which is exam score, is affected by anxiety scores, our spent revising, and A-level entry points. And remember that there is always an error term. So now I guess we are ready to do the analysis. I will be super slow in doing this, so just to make sure that everyone is following up. So if we want to do the analysis, just go to analyze, then regression, then linear. Again, so if you just click on analyze, regression, and linear, a linear regression window will pop up, and you want to move exam scores into the dependent and all other variables in the independent block. So you are going to do this. And as I said before, before moving on, I just want to make sure everyone is with me. Is there anyone behind us? Okay, no answer. I will assume that everyone is following us. Okay, so as I said before, we don't have to really pay attention before doing any analysis for the assumptions, since that SPSS gives us the option to decide which assumptions should be assessed during through this window. So if you click on the first one, the statistics, the first button here, you want to keep estimates and model fit, and you want to add or click on Durbin-Watson statistics. And Durbin-Watson statistics is just simply the statistics that assess the autocorrelation assumption. So this is why we want to include this. We want to include some descriptives as well. And of course, the collinearity diagnostics, in which we will assess the collinearity assumption through it. Is everyone following? If there is no answer, I will continue. Great, I'm getting yeses. So let's go, just hit on continue and then move to the second button, which is the plots. in plots, we want to assess the normality assumption and through histograms, a normal probability plot, and we want to also assess the homoscedasticity assumption. So in this window, we want to move z residuals to the y-axis and z predicted to the x-axis. Again, I'm going to do this again. So we want to move z residual to the y-axis and z predicted to the x-axis. And then just click on histogram and normal probability plot to get some plots. Is everyone following me? Okay, so I think everyone is following me. Let's move. So click on continue. We will not play with the method. So method is basically, we have so many options here. Enter is when you want to add all of your variables into the model without removing any of them, or without asking SPSS which predictors are the best fitting in my model. So basically, we are forcing SPSS to include all of the predictors that we want. So by choosing different type of method like stepwise or remove, backward or forward, those are kind of the variable selection approach of using linear regression in SPSS. So just keep it enter and then click on OK. You should got some tables. Is everyone able to see my output window? Great. Is there any error? I hope everyone gets the same thing. Okay, great. So let's move on. First, can I enlarge? Sure. I don't think that it's going to enlarge itself. So is this looking fine for you? Great. Okay, so the first table in the output is some descriptive statistics. So just give you the mean for the participants, for the exam score, standard deviation, and the sample size, so on for other variables as well. The second output is the correlation table. So the correlation table is just the normal Pearson correlation table. Just tells you which variables are highly correlated to each other and whether the correlation is significant or not. So if you look at the exam score, you can definitely see that it's highly correlated with hours spent revising, with A-level entry points as well, but it's not highly correlated with an anxiety score. And it's not significant as well. This is what we actually want from this table. So if we move to the third table, These tables specify which variables are into my model. So if you can see that all this sentence telling you that all requested variables were entered in your model, since that you choose the enter method of adding variables. Okay, so this is the fourth variable. The fourth table, the model summary table. We want to talk about three things in this table. First of all, the R value. R is the multiple correlation coefficient. As it approaches 1, meaning that it's a very good model. However, the interpretation of R sometimes could be misleading. So we usually rely on R square. So 0.86, when we convert it to a percentage, it should tell us that the model explains 86% of the variation in our dependent variable. So this is how we interpret the R square value. And sometimes we add so many predictors in our model. So adjusted R square will be the best value that you should report in your study. So adjusted R square is just adjusting for the number of predictors in your model. So when you have so many predictors, R square could be misleading. So you should definitely report adjusted R square in the same way of reporting R square. So we can, if we rely on adjusted R square here, we should say that 83.4% of the variation in the dependent variable is explained by our model. Okay, let's move to the Durbin-Watson statistic. So Durbin-Watson statistic is basically used to assess autocorrelation. I should mention that Durbin-Watson statistic ranges from 0 to 4. If this statistic is equal to 2, this means that there is no autocorrelation problem and the assumption is met. As we approaches 4, this indicates that the residuals or errors are negatively correlated with each other. On the other hand, as we approaches 0, this indicates or give us a sense of the idea that residuals or errors are positively correlated to each other. And in either cases, the assumption is violated, meaning that there is a problem of autocorrelation here. So how large the value should be and how small the value should be to say that there is a problem? So as a rule of thumb, any value larger than 3 or below 1 should pay your attention. So in this case, 3 is acceptable. However, I will say from my perspective that there is a violation for the autocorrelation assumption. And we can say that the residuals are dependent. So the independent errors assumption is violated from my perspective. So let's move to the ANOVA table. The ANOVA table just give us an idea about the overall model, whether it's explain the dependent variable significantly or not. So if we want to differentiate between the model summary and the ANOVA table, the model summary just if we care about these two values, it just give us an idea about how much variation and the dependent variable is explained by the model. However, in the ANOVA table, we will know whether the model significantly explained this amount of variation or not. So by looking at the F value and the significance, we can say that this model is significantly, the overall model significantly useful in explaining the dependent variable, which is exam score. And the first degree of freedom is 3, and the second degrees of freedom is 16, and the F value is 32.81. We can clearly see that the significance level is less than let's assume that our alpha level is 0.05. So this is far below 0.05, and therefore it's significant. Is everyone following me here? Or I should be slower? Good. Don't worry about the interpretation of the tables, because you are going to see them in the slides. Yeah, so they should be on the slides, so don't worry about it. So again, the ANOVA table just give us an idea about whether the model, the overall model, explains the variation in the dependent variable significantly or not. Okay, so let's move to the coefficients table. It's my favorite table. So we want to know 3 things from the coefficients table. First of all, we will talk about the collinearity statistics, and it's the statistic that assess the collinearity between predictors. Usually, we rely on the last column, the VIF statistic. As a rule of thumb, any value larger than 10 indicates that there might be a violation for the collinearity assumption, and therefore there are at least 2 variables who are perfectly correlated with each other. So we have to revise our predictors again and to look at the correlation coefficient between all predictors to see if they are highly correlated with each other or not. The tolerance is actually the same thing. The tolerance is simply the reciprocal of VIF. So if you just do 1 over 2.28, you will get this value. So I think VIF is kind of easier to interpret. So this is the collinearity assumption, and this is the first thing we got from this table. Again, any value larger than 10 indicates that there is a problem. So we are good to go here. The second thing we want to get from this table is the significance of the effect of each predictor in the model. So we know previously from the correlation matrix that exam scores is perfectly related or highly correlated with hours spent revising and A-level entry points, but it's not with anxiety. So this could give us a sense of this result. And we can see that hours spent revising is a significant predictor. Anxiety is not, because the value is larger than 0.05, and we fail to reject the null. And we also can see that A-level entry points is also significant. So the effect is significant. So this is the second thing we want to know from this coefficients table. The third and the last thing we want to know from this table is the unstandardized coefficients, or simply the coefficients. So the coefficients, the way of interpreting coefficients is if there is a 1 unit increase in hours spent revising, the exam score will increase by 0.55 unit. So if I move to the slides, I think it would be easier for you to look at it. So if you look at the hours spent revising, the coefficient is 0.55. So we can say that with 1 unit increase in the hours spent revising, the exam scores will increases by 0.55. And I also have to mention that this is true if everything else is held constant. So anxiety will be constant, the intercept will be constant, and the A-level entry points will be constant as well. So for an anxiety, let's say with 1 unit increase in an anxiety scale or score, the exam score will increase by 0.1. However, this increase or this change is not significant. So this will help us later on if we want to do kind of a write-up, APA style write-up to summarize our findings. Lastly, the A-level entry points, the same way of interpretation. I just want to pay the attention for the plus sign here, the positive sign. So the positive sign will lead to increase, but the negative sign will lead to decrease. So let's assume that the A-level entry points coefficient is negative. So we will interpret this as with 1 unit increase in A-level, the exam score will decrease by 1.99. So the constant means, is the constant means minus 11? No, this is actually the intercept. So if you want to write the prediction equation will be the intercept value, the coefficient of the intercept, plus the coefficient of the hours spent revising times the value of hours spent revising. So the coefficient is kind of the weight in this equation, and so on for other variables. Is it clear before moving to the plots? Good. Okay, so let's move to the, there are also some statistics about residuals. We usually care about the collinearity diagnostics if there is a violation in the VIF scores. So we don't look at this table usually if the VIF is below 10. Okay, so let's look at the first plot or chart. So this chart is assessing, or we can assess the residuals normality assumption through this chart. So because of the small sample size of 20, you can see that the line is not fitted very well. So However, we can see that there is nothing super crazy, and we might be 100% sure that there is no violation for the normality assumption. And to be 100% sure, we can also look at the normal PP plot. So if the points are fitting this line, we can say that the normality assumption is met. However, we can see that there are some deviations from the line. However, they are not, let's say, super crazy. So we can accept that. We can say that, yeah, this is kind of looking normal, and therefore we are good to go. The last chart is to assess the homoscedasticity assumption, which is you should not see any pattern. You can clearly see that those points are randomized, so there is like no pattern. They are not straight line, they are not decreasing, they are not increasing. You can see them everywhere. So as the result suggests that there is no pattern, we can conclude that the homoscedasticity assumption is met, and therefore everything looks fine. So this is how you perform the analysis through SPSS, and therefore you are ready to write your APA style report for your study. Again, don't worry about the interpretation. You will see them on the slides. Okay, so if we want to write everything in an APA style format, first we will say that a multiple linear regression was fitted, as we did. To do what? To explain the exam scores based on 3 variables. I mentioned them, so on hours spent revising, anxiety scores, and A-level entry points. All of the assumptions were met except the autocorrelation assumption between residuals, we get the result from the Durbin-Watson statistic, if you remember. I said that from my perspective, this is a violation. So it depends on the researcher himself, I would say, and the resource that or the reference that you have. Okay, so we talk about the model, we talk about the variables in the model, we talk about the assumption, then we have to move to the results. So the overall model explains the R-squared value variation of exam score, and it was whether significant or not. And in our case, it was significant, useful in explaining the dependent variable. And here's the F value, first degree of freedom, second degrees of freedom, and the F value, which was found to be less than 0.05, or the p-value was less than 0.05. So we, in the first paragraph, we talked about the overall model. In the second paragraph, we will talk about each variable or each predictor. So as you saw earlier, with 1 unit increase in hours spent revising, the exam scores increases by the coefficient, and you should also say whether this change is significant or not. So in the hours case, it was significant. This was the t-value, and the degrees freedom for the t-value is always the second degrees freedom from the F statistic. So in this case, it's 16. And this is the t-value, which was found to be significant, and the p-value was less than 0.05, and so on for other variables. You may want also to add the prediction equation, which was here. Sometimes some reviewers may ask you to provide this as well. Okay, any questions so far? What's the difference between the R squared and adjusted R? This is a very important question. So sometimes you add so many predictors in your model. So if you report the R square value, it might be misleading. So you want to add the adjusted R square, since that it is adjusting for the number of predictors. So I would say that it is a better way to report your findings. You're welcome. So no other questions. Let's move on. So this is one way to benefit from the linear regression analysis through SPSS. The second approach is, what if we are interested in knowing the best predictors to include in our model? So in the previous example, we add hours spent revising, anxiety scores, and A-level entry points to see whether they have an effect on exam scores or not. However, sometimes we are not sure which predictors are the best for our model. So we want to go through this approach in which we will use different variable selection method when we want to run the analysis. So let's go back to SPSS, and sorry, let me just minimize this. Are you able to see my SPSS screen? Great. So let's do this. Go to Analyze, then Regression, then Linear. The same process of performing the regular analysis with putting every variable in the model. Okay, I just want to reset this one. You don't have to, but I don't want so many tables. So again, exam score as the dependent variable, all others as IVs, independents. You have different variable selection methods here. If you just click on enter, you will see a drop down menu and you can choose different methods. For me, I really like the forward method. So it's basically adds the most I would say the best predictor first, and then the second, and there are some criterion that should met before adding the variable into our model. So okay, without adding anything else. Okay, now you can see different tables. The first table had different number of model. So for example, in the first model, like for example, here we have two models. The first model has only one variable entered, which is the A-level variable. And it's not surprising, Since that, if we go back here, we can see that the coefficient of A-level entry points is the largest. So it adds the first variable first by forward method using the criterion probability of F value to enter, which is 0.05, less than 0.05. In the second model, it adds hours spent revising. So the second model has two variables, A-level entry points and hours spent revising. So in each model, it just adds one to the previous one. So on the previous one, we had the A-level entry points. In the second model, it just adds the new variable, which is the hours spent revising. You can see that the anxiety was excluded or dropped down from the selection, meaning that it didn't meet the criterion here. So always the second model or the last model, it's not always the second, but the last model is the best usually. So you can see that the second model here has A-level entry points and hours spent revising, and it explains 83% of the variation in the dependent variable, compared to the first model, which only adds, or which only explains 76% of the variation. So yeah, we will move forward with the second model. And you can see that we have an excluded variables table here. And you can see that in the second model, we didn't include the anxiety, or it didn't include the anxiety score, since it has a very low coefficient. And that's it. This is the second approach of, or the second benefit for using multiple linear regression window in SPSS. So any questions here? And I think that to cover different type of variables, different type, I'm sorry, for methods to add the variables, we should have another webinar. So this is kind of an introduction to that. And we will always be happy to assist you if you have any further question about the methods of including variables in your model during our hours in the Statistical Supporting Unit, which you can find on our website. Me and Trent and everyone else will be more than happy to assist you. Okay, so it seems like no questions. Let's move on for this exercise. I will leave this exercise for you guys to practice the multiple linear regression analyses through SPSS. So we want to determine whether GRE variable and quantitative scores have any effect on GPA. So if you want, you can download the data set from this link, which I will post in the chat. So I'm sorry, how would I? Okay. So this is the link. If you want to practice this. And finally, I hope you guys enjoyed the webinar. I hope that I was not super fast. I hope that I went through everything. And thanks for your listening and choosing to attend this webinar. And please, if you have some time to fill a survey about this webinar, and it should definitely help us to evaluate our performance and take your feedback into consideration for any future webinars. So we will definitely appreciate your time if you fill out the survey. And again, before ending this webinar, we will always be happy to assist you during our time or hours on the Statistical Supporting Unit website. And feel free to reach out to us. And I wish you a very good day, and stay safe and take care. I'm sorry, just before moving, I will just share the Statistical Unit website. So this is the one, and the slides, yeah, will definitely be posted on the website. So if you just scroll down, you will see the webinar slides down there. Have a good day.